So we're going to assume here that we have a mirror shaped like a section of a sphere. Not the entire sphere itself, but let's say we take this, this hypothetical sphere. I'm going to mark the center of it because we're going to want to refer to that later. Let's say we've got a line through the center here. Looks good. And another line through the center here. A couple of diameters will determine where the center is. So there's the center of the sphere. So you've just got this sphere. Let's say it's coated inside and out with some sort of silvery, shiny material so it can reflect light. And let's say we cut off a portion of that. Let's say we slice off just this arc. So this arc is all we've got. I guess that means I'll need to redraw the lines here. There we go. So we've got this, this bent mirror that's shaped like a portion of a sphere. And we can mark the center of that and any lines through the center we want. What's going to happen here, if we send in rays of light, like let's say we send in a ray of light that is going along this center line, which we usually call the optical axis. So the optical axis or the central axis is this line straight through the center of the mirror itself and perpendicular to it at that point. So if you send in this ray of light that hits the mirror exactly in the center where it's perpendicular, what's going to happen to that incoming ray of light? Yeah, that's going to get reflected back. Exactly. It just gets reflected straight back. In general, any ray of light that comes in along a normal line, that is a line straight line perpendicular to the mirror surface at that point, is going to get reflected straight back with no modification in direction. But let's say we have another ray of light that's also parallel to the central axis, and it hits the mirror here. What would you expect to happen to that? Would you expect that to reflect straight back? Or would it reflect and bounce upwards? Or it would reflect and bounce downwards? What do you think is going to happen there? Yeah, that's going to reflect and bounce downwards. And we can see why that is by drawing in what we call a normal line. A normal line just means a line perpendicular to the surface of the mirror at that location. And one of the convenient things about a spherical mirror is that any normal line, any ray of any line that's perpendicular to the surface is guaranteed to go through the center of the sphere. Any radius vector or any radial direction, any line through the center is going to hit the surface at a right angle. So for a spherical surface, it's very easy to draw in a normal line. It's just going to be a line through the center and through that point. So this is what we call the normal line. And we're going to use the normal line to measure angles. The angle we care about, and this is true for both refraction and reflection, the angle we care about is the angle measured relative to the normal line itself. This angle would be called the angle of incidence. Angle of incidence just means the angle that the incoming ray of light makes with the normal line. And it's tempting to want to measure the angle that the ray of light makes with the surface itself. But mathematically, it turns out to be very inconvenient to try and define an angle between a line and a surface. It's much easier to define an angle between a line and another line. So if you create a line that's perpendicular to the surface, the normal line itself, we can define the angle between the ray of light and the normal line. And the important thing about reflection is that when the ray of light bounces off, it's going to bounce off the mirror and make the exact same angle with the normal line. that this new angle, the angle between the reflected ray of light and the normal line, also called the angle of reflection, is going to be the exact same angle. So this is the general rule for reflections. The angle of incidence and the angle of reflection should be the same angle. And ultimately, that's just because the light is not changing what material it's in. It starts off in air, bounces off the mirror, it's still in air, so it's still going to make the same angle. Any questions on that so far? And of course, this ray just keeps going. And if we put in another ray of light, let's say we have another ray that's higher up. This ray of light is going to hit the mirror here. We can draw in another normal line at this new location. And again, for a spherical surface, every normal line is going to be passing through the center of the sphere itself. This one makes a larger angle of incidence, and it's going to make a correspondingly larger angle of reflection. So it's going to bounce off, making the same angle. And it so happens that with this spherical mirror, this reflected ray also passes through that same intersection point. In fact, it turns out this is true for any ray of light that starts off parallel to the optical axis. Even if we start off below the center, if you've got this incoming parallel ray, it's going to hit the mirror and bounce off. And in this case, I don't even need to draw out the normal line. The general pattern is that any incoming ray that's parallel to the central axis is going to bounce off straight towards that same intersection point. So all these incoming parallel rays bounce off straight towards and through that one point. And what do we call that one point? Yeah, this point is the focal point, or the focus. This is how we define the focal point. The focal point is this one location that all of the incoming rays of light, or all of the reflected rays, pass through if those reflected rays came from parallel rays originally. So any ray of light, let me make that a different color. Any ray of light that starts off parallel to the central axis is going to bounce off to become going through this focal point. So this is how we define the focal point. If you've got this mirror shape like this, and we would call this concave because from the side the light is on, it's caved in. All these parallel rays of light are going to hit the concave mirror and bounce off towards this one point. And since it's making all these rays of light converge together, we call this a converging mirror. And I want to make a distinction there. We could call this a concave mirror. We could also call this a converging mirror. Concave is a description of the shape. Converging is a description of the behavior. And I would say the behavior is really the more important one of those. The shape is only really important in the sense that it leads to this behavior. But what we care about for any mirror or any lens is what it does to light. So I would describe this mirror as a converging mirror whose shape happens to be concave. But the concave shape is what leads to the converging behavior in this case. Any questions on that so far? So as a general rule, for any converging mirror, because of its concave shape, any ray of light that starts off parallel to the axis is going to bounce off to become going through the focal point. But all of these paths also work in reverse. We can say that any path that starts off parallel to the axis ends up going through the focal point. But we can also reverse that. Clear this up a little bit. We can also reverse this and say that any ray of light that goes through the focal point would have to do what as soon as it hits the mirror? Yeah, that's going to bounce off to become parallel to the central axis. And that's true for any ray of light that comes out of the focal point, or even if it didn't start from the focal point. Let's say you've got a ray of light from somewhere else that passes through the focal point. That ray of light is going to bounce off to become parallel. Or even if it didn't pass through, let's say you got a ray of light that started at this location, but it's going straight away from the focal point. The fact that this ray of light is at least on a line, we may as well use the term collinear. This is a ray of light that is collinear with the focal point. Any ray of light that is collinear with the focal point, whether it's actually passing through it or not, is going to hit the mirror and bounce off to become parallel. So this is the general rule for any converging mirror. Any ray of light that starts parallel bounces off and goes through the focal point. Any ray of light that starts collinear with the focal point, whether it passes through it or not, is going to bounce off to become parallel. Any questions on those rays of light so far? And the nice thing about this approach is it means that for these special rays of light, these rays of light that are easy to draw in because they're either collinear with the focal point to start with or they're parallel to start with, we don't actually need to draw in a normal line. We can just say, oh, it's going through the focal point, so we know it's going to bounce off to become parallel. Or it starts off parallel, so we know it's going to bounce off through the focal point. One other important thing to notice here, compared to the rest of the sphere, where is the focal point? In fact, let's look at the rest of the sphere here. Yeah, the focal point is exactly halfway from the center to the surface, half of the radius. I might not have drawn that absolutely perfectly here, but in general, the focal point should be exactly halfway between the center and the surface. So that distance, and we're going to be measuring all of these distances from the surface of the mirror. This distance is called f, the focal length, and that's going to be exactly half the radius. The radius of that sphere that the mirror was cut from. So let's try applying this to an object. Let's say we have an actual physical object somewhere over here. So this is just some object, and we assume that the object is emitting light. It doesn't necessarily have to be creating light. Presumably it's just reflecting light. Like we've got this object, sunlight's shining on it, the sunlight bounces off the object, but we can treat the object as the source of the light. In fact, that's essentially how we're going to be defining object here. Object means the point that the light is actually coming from. And the object is emitting light in all directions. We can focus on just the light coming from the top of the object and assume everything else follows the same pattern. So we've got light coming out of the object in all directions, but we only really care about which directions. What directions are going to be the easiest to keep track of? Yeah, we can start with the one that goes to the focal point because we don't need to keep track of all of them. We can just look at what we call the principal rays that are easy to keep track of. So let's say we have a ray of light that goes through the focal point because one of them will. What do we know about that ray of light? That's going to bounce off to become, yeah, that bounces off to become parallel. And we can also draw another one that starts parallel and then does what? Right, that's going to bounce off through the focal point and keep going. And there's also another one we can draw in. You really only need two of them, but it's sometimes useful to draw in a third one to be sure. Specifically, if you draw a ray of light that passes from the object through the center of the sphere, not the center of the mirror, but the center of the sphere, how would you expect that to bounce off? Right, that's going to bounce straight back. Because like I mentioned earlier, any line that passes through the center of the sphere is a radial direction, radius, diameter, whatever you want to call it. It's going to hit the surface at a right angle, perpendicular, so it's going to bounce straight back. And we've got a slight problem here because really those reflected rays should all intersect at one point. So I'm thinking I didn't draw the focus exactly halfway in between here. Let me modify that slightly. Let's say the focus is more halfway in between. So I'm just going to modify this a bit to make this more accurate. There we go. So if I draw this more accurately with the focal point actually halfway between the surface and the center, it looks like those three principal rays, the rays of light coming out that are easy to draw out, the one that starts parallel and bounces off through the focus, the one that starts through the focus and bounces off parallel, and the one through the center that hits the surface and bounces off exactly the way it came. And also one other that can sometimes be useful to draw. If you draw a ray of light from the object, not towards the center of the circle, not the center of the sphere, but instead towards the center of the mirror surface itself, like where the optical axis hits the surface, that's going to bounce off with the exact same angle. Because in that case, the optical axis is the normal line. So the angle that the ray of light makes with the optical axis is the same as the angle that the reflected ray is going to make. Those are all going to meet in one point, which means if you, as the observer, are standing somewhere else, let's say you're the observer and you're standing over here. As the observer, you would see these rays of light. These rays of light are coming from here and they hit your eyes, and your brain thinks, those rays of light must have come from what point? What point does your brain think these rays of light are coming from? If we just ignore everything else for the moment, yeah, ignoring everything else, if all you see is these rays, your brain thinks, oh, those rays must have come from this location. That location where all the reflected rays seem to cross, or where they all seem to come from. As far as your brain can tell, your brain is just thinking, oh, we've got this ray of light, and this ray of light, and this ray of light, and this ray of light. And your brain thinks, oh, those rays must have come from this location. Because your brain naturally and quite intuitively, I think, tends to think of light as traveling in straight lines, which most of the time it does. But that doesn't take into account the fact that sometimes light bends. So your brain thinks it sees an object here. But that's not actually the object. And I'm drawing this upside down because the rays of light crossed at a point under the axis. That's not actually the object, though. That's just where all the rays of light seem to come from. So what do we call that location? That location that the final rays of light seem to come from is called what? Yeah, this is what we call the image. The image is that location that all of the final rays of light after the reflection seem to come from. And they didn't actually come from that point. They just passed through that point. But that's the point where all of the final rays of light seem to come from. So that means when you look at this mirror, you're going to see what looks like this ghostly object floating upside down in midair. And of course, there's nothing really there. That's just where all these final rays of light seem to have come from. And what would we call that type of image? If the rays of light really did pass through that point, how do we describe that? Yeah, this is a real image. Image means it's the location that the final rays of light seem to be coming from. Real image means that, yes, the rays actually did pass through that point. Any questions on that so far? And we can actually throw in some numbers here as well, some mathematics. The distances we're going to be caring about are the distance between the, and again, we're measuring these all from the mirror itself. Distance from the mirror to the object, we're going to call O, the object distance. And then the distance from the mirror to the lens, we're going to call I, the image distance. So these are all measured from the surface of the mirror itself. And have you seen an equation describing how those are related to each other? It's the universal, we usually call it the thin lens equation, but it applies to both lenses and mirrors. Yeah, exactly. So the lens and mirror equation. 1 over F equals 1 over I plus 1 over O. So if we know any two of those, we can immediately find the third. So let's try this out. Let me just make up some numbers here. Let's say we already know that the focal length is, let's say, 6 centimeters, and the object distance is, it looks like about 3 times as far, let's say 18 centimeters. And we want to find where the image appears. So we can do that just by substituting these into the equation. We can say 1 over 6, and I'm going to leave off the units for now because everything's going to be in centimeters anyway. 1 over the unknown image distance and 1 over 18. How would you then solve that for I? Yeah, subtract the 1/18 from both sides. So I'm going to try writing this in a different format. Let me stack the fractions. That'll make it easier to see what's going on. Equals 1 over the image distance. And then how would you combine the 1/6 and 1/18? How do you turn the 6 into 18? Yeah, multiply. And we can do the same thing as long as we're doing the same thing to the numerator and denominator. So multiply the numerator by 3 and multiply the denominator by 3. And there we go. So that'll be 3/18. Yeah, there we go. 3/18 minus 1/18, so that'll just be 2/18. So that reduces to 1/9 equals 1 over I. So what does I have to be? Yeah, I is going to be 9, and that'll be centimeters. So that tells us that the image occurs at a location of 9 centimeters from the mirror. And that's specifically positive 9. For image distance, positive and negative basically tells you which side of the mirror or which side of the lens. And there are some rules for that that make it seem like lenses and mirrors behave in opposite ways. But the general rule that works for both is that for the image distance, A positive value means the direction that light is traveling. At the end, like after everything, after it hits the mirror or lens. So in this case, we've got light going from the object, light goes to the left and bounces off to the right. The final rays of light are traveling to the right, so we're going to treat to the right as the positive direction, which means a positive image distance means an image on that right side of the mirror, the side that light is traveling on. So in general, if the image distance is positive, that means image on the side of light traveling. Whereas image being negative would mean the image is on the dark side of the mirror. It's on the side opposite to the direction light is traveling. So that would be, in this case, an image behind the mirror. And as long as you keep those in mind, this should be true for both mirrors and lenses. Positive value for I means the image is on the side that light is traveling at the end. Negative value for I means the image is on the side opposite to the direction light is traveling. Any questions on that so far? So we know where the image is, 9 centimeters from the lens, and note that that's a little bit further than the focal length itself. In fact, focal length and a half. So that looks remarkably similar to what we got from the ray tracing itself. The ray tracing is a great way to get a conceptual idea of what's going on and what sort of values you should expect. The equation should give you exact values though. So I think if you have time, it's a good idea to look at both, but either one gets you some useful information. Any other questions on that so far? Also, have you seen the idea of magnification? How do we define magnification here? What does magnification mean? Like, how would you calculate the magnification in this case? Yeah, it's the ratio of heights. The ratio of height of the image. So image height over object height. So if M is, let's say, exactly 1, that means the image and object are the same height. If the magnification is greater than 1, that means the image appears to be larger than the object. If M is smaller than 1, then the image is smaller than the object. In this case, it looks like the image is smaller than the object itself, so M should be smaller than 1. Also, the image is upside down. How do you think that would be represented in the image height? How would you represent a height that is upside down, a height below? Yeah, we describe the height as negative. So the image height, usually written as just h sub I, is going to be negative here. And the object height is going to be positive because the object is above the central axis, but the image is below the central axis. So we treat that as having a negative height. Negative height means upside down. In this case, though, that's not very useful yet because we don't know how tall the image is. We might know how tall the object is. Let's say we know the object is, let's say the object is 5 centimeters. Well, it's not really good, 5 centimeters. Maybe, you know, let's say about 5 centimeters tall. Let's say the object happens to be 5 centimeters tall. We don't know the image height, though, and we also don't know the magnification. But there's a very useful fact we can use here, a bit of geometry. If I draw in this diagonal line, and also this diagonal line, that's the ray of light that just reflected at what angle? What do we know about the angles that those lines make with the central axis? Yeah, they're equal, right? This angle and this angle, those should be equal angles, which means that if we draw out these two triangles, those two triangles are going to be similar because they both have these angles being the same and they both have these right angles. So these are similar triangles, and similar triangles have to be proportional to each other. So the ratio of, let's say, image height versus object height has to match the ratio of image distance horizontally over object distance. So this is really the key to the idea of magnification. The image height over object height has to match the ratio of image distance over object distance. In this case, for instance, what is the image distance over the object distance? And since we have both of those, right? We know the image distance, we know the object distance. What's that ratio going to be? Yeah, the ratio image over object in terms of the distances, 9/18, that's 1/2. So we know then that the magnification factor is 1/2. However, the image is also upside down, so we're going to need a negative there. And in order for that to work, we actually need a negative in the formula itself. So we're going to describe the magnification formula. The definition of magnification is height of the image over height of the object. But it also is true that the magnification equals negative image distance over object distance. So the height of the image, the ratio of heights, height of the image over height of the object, is the definition of magnification. We also know that the magnification happens to equal negative image distance over object distance. So those ratios have to match except for the negative sign. In this case, we can say that the magnification is negative 9/18. That'll just be negative 1/2. And that's unitless since the centimeters and centimeters cancel out. And then we can take that back to the definition. Now that we know it from the formula, the magnification equation, we can say that's equal to height of the image over height of the object, which we know is 5 centimeters. So what can we now solve for? What's the only unknown left here? Yeah, height of the image. All we need to do is multiply both sides by 5. Negative 1/2 times 5 centimeters would be negative 2.5 centimeters. So that tells us the image is 2.5 centimeters tall and upside down. In fact, a real image is always going to be upside down because it's going to be on this side that light reflects back to, and the light reflecting back bounces to the other side of the optical axis. So in general, a real image is going to have a positive value for I and an upside down height. Whereas a virtual image on the back side of the mirror is going to have a negative value for I, but it'll be right side up. Any questions on that so far? So let's see if we can set up another example that's going to lead to a different image. Let me clear out these rays of light. And let's put the same object at a different location. If we move the object around, that's going to change where the image is and how big the image is. But let's go to the extreme. Let's put the object really close to the mirror. and try drawing out those rays of light. Let's say the object is at maybe 4 centimeters. And we may have to move this a little bit. I need some more room. Okay, so let's say we draw in the same ray tracings. Drawing in the ray tracings here, what ray of light could we start with? What are some rays of light that are going to be easy to draw in here? Yeah, we could draw one that starts off parallel and then does what? Yeah, that'll reflect through the focal point. And then what else could we draw? We can't really draw one that goes towards the focal point, right? Because that's never going to hit the mirror. So what should we draw instead? Remember, the ray of light doesn't actually have to pass through the focal point. It just has to be collinear with the focal point. So let's say we just have this line through the focal point. Any ray of light that passes along that line, whether it actually goes through the focal point or not, is going to follow this pattern. So let's say we draw in a line from the object along that line. That is, even though it never actually passed through the focal point, this is a ray of light that's collinear with the focal point. So what's that going to do? That'll bounce off to become any ray of light that starts off collinear with the focal point, even if it doesn't actually pass through the focal point, is going to bounce off to become parallel. Let me draw these ones a little thicker as well. Starts off parallel, bounces off through the focal point. And yeah, we could also draw one from the object straight towards where the optical axis intersects the mirror. And this one can be kind of tricky to draw out because we got to draw the same angle. But sometimes that can be useful to just sketch anyway. And also we could draw one that starts off collinear with the center of the sphere itself. So a ray of light that's collinear to the radius vector, the radius line. If we've got this ray of light from the object straight out from the center of the center of the mirror sphere, what's going to happen to that one? That just bounces. Yeah, that bounces straight back the way it came, through the center of the sphere. So we now have 4 principal rays, 4 rays we can draw out. Are those rays going to intersect on this side? No, there's no intersection at all. But as the observer, you still see, here's these rays of light. So ignoring everything that happened before that, ignoring all this, all that you as the observer notice is, here's these rays of light. And your brain thinks, well, rays of light travel in straight lines all the time, right? These rays of light must have come from somewhere. Specifically, they must have come from way back here. Yeah, they must have come from somewhere behind the mirror. And of course, they didn't actually come from back there, but they all seem to have come from back there if we backtrace these rays of light. And these aren't all exactly accurate, but I'll fudge it a little bit. Close enough. So this point right here behind the mirror is going to be what we call the image. We get an image at this point behind the mirror. And what kind of image would we call that? if the rays of light seem to come from that point but didn't actually pass through that point. Yeah, this would be a virtual image. It is an image because that's where the final rays of light seem to come from. It counts as a virtual image because the rays of light didn't actually pass through that point. We had to backtrace to get there. So that would be the virtual image. And we could do the same sort of numerical analysis as well. If we actually plug in these numbers to the thin lens or thin mirror equation. So going through the exact same procedure, we still have 1/6 as the focal length of the mirror, but now the image distance is 4. So we'd subtract 1/4. And there's actually an easier way to do this. Instead of running the numbers and solving it every single time, we're going to be using the thin lens / thin mirror equation over and over again. So instead of having to plug in the numbers and solve for I every single time, because you often want to solve for I, let's try solving for I once and for all. We got 1/f equals 1/I plus 1/O. If we wanted to just solve this for I, what would we have to do? How would you isolate I here? Yeah, we could start by subtracting the 1/O from both sides. Yeah, this is a bit of a mess. I'll tidy this up in a moment. There we go. So 1/f minus 1/O equals 1/I. And then in order to do anything useful with this, we really need to combine these into one big fraction. How would we combine 1/f minus 1/O? How could we get a common denominator there? This first one, for instance, 1/f, that's missing an O. And the second one, 1/O, that's missing an F. So let's just multiply those in. Let's change 1/f into 1 times O over F times O. Multiplying the top and bottom by O means we're not actually changing anything. And then the second fraction, the 1/O, let's just multiply that by F over F. Multiplying the top and bottom by the same F means we're not actually changing anything. But we are changing both of these to now have the same denominator. So now we're just subtract the numerators, O minus F over O times F. So O minus F over O times F equals 1/I. And then what's the only other thing we still need to do to solve for I? Yeah, we just flip both sides of the fraction, or flip the fraction on both sides, invert both sides, and we get image equals O times F over O minus F. So we now have a general formula for the image distance. And note that this should work for both lenses and mirrors, because the original equation works for lenses and mirrors. In general, if you're just trying to find the image, you can start here. You can start with I equals O times F over O minus F. And that's a very useful shortcut, because it means you can just plug in O and F and immediately get the value of I. Let's try that. I equals O times F, that's 6 centimeters times 4 centimeters, divided by O minus F, that's 4 centimeters minus 6 centimeters. Simplify that, we've got 6 times 4 is 24, divided by -2, till we get -12 centimeters. So that's the image distance, negative 12 centimeters. 12 centimeters from the mirror. And what does the negative sign mean? Where would we expect that image to be? 12 centimeters, yeah, 12 centimeters to the opposite side, or 12 centimeters on the dark side of the mirror, the side opposite the direction light is traveling. So, and that's exactly what we have. The virtual image, and I didn't really get this very well to scale, so that's not exactly 12 centimeters like it should be, but it's definitely on the back side of the mirror. So that's a virtual image, a negative value for I, signifying that it's on the opposite side from the direction light is traveling. And we could also find the magnification factor. If we take the image distance divided by the object distance, 12 over 4, 12 over 4 is 3. So that means the image is 3 times as tall as the object. And the negatives cancel out, making it positive, meaning the final image is right side up. So that's an upright virtual image, 3 times as large as the object, 12 centimeters behind the mirror. Any other questions on that? All right, on your own, to get some more intuition with this, try practicing this with similar examples, but different layouts. Like try putting the object even closer to the mirror, or even farther from the mirror, or really close to the focal point, or on the focal point. And try it with a different mirror also. There's different but slightly similar rules for a convex mirror, if the rays of light come in and diverge instead of converging. So try applying the same ideas to a diverging mirror, which is going to have different behavior of the rays of light. A good way to get some intuition with this. How do we know it was upright? In terms of the diagram, because the rays of light intersected at this point above the optical axis. And in terms of the equation, because we ended up with a positive value for M. If you actually plug in negative 12 for I and positive 4 for O, the negatives end up canceling out and you get a positive value for magnification. And that means it is not flipped over. All right, so get some more practice with that. Develop as much intuition as you can. Ideally, you want to get to a point where you can just look at a situation and get a general idea just from looking at it. Oh yeah, that's going to make a virtual image. Or, oh yeah, that's going to make an image that's smaller or larger than the object or whatever. So get some practice with that and let me know if you have any questions, and I will see you next time. You're welcome.